Okay, so today we're going to talk kind of like we did in last Friday's lecture about how we implement methods for solving these trust problems in sort of an algorithmic context. But the algorithms that I'm going to lay out and how it maps to how you might implement this in a MATLAB code or something like that are going to be also generally useful if you're trying to solve these problems by hand. So it gives you a step-by-step procedure through which you can kind of follow a similar approach if you had to solve it by hand. And to give you a little bit of a jump on things, I've also uploaded the next homework assignment. I know you're thinking, oh, well, homework assignment two, it isn't even due yet. But I think we're kind of I would say a little bit ahead of schedule. So I think we're on track. If you want to take a look, homework was posted yesterday evening, and part of that assignment actually includes similarly implementing some of the functionality that we'll discuss in today's lecture. And the intention is really to demonstrate that the methods and everything are pretty much the same in terms of how you would go about solving these problems and kind of implementing a finite element method. A lot of the steps are the same. There's only just a few minor modifications that differ from what you're kind of used to seeing in the case of, one-dimensional finite element context. So we'll kind of step through and show where those differences arise, but otherwise it's going to be essentially the same sequence of steps that you would follow. Very similar looking kind of MATLAB-based program if you were to implement this. And the intention is to show that really the methodology is very generic and kind of can be extended to accommodate these multidimensional problems as kind of a generalization. All right, so let's start off first by defining some kind of trust problem that we're going to try to solve. And as we talked about in last Friday's lecture, really we need to just define things like what's the geometry of the problem we're solving, what are the constraints, the supports or the displacement boundary conditions, and what are the external forces we're putting on the structure, where we've assumed those external forces are only applied at the joints, so we don't have to worry about distributed loads now. That was kind of tricky, and it's still sort of maybe a detail you're working through in homework assignment number two. But thankfully, in the case of trusses, we're just going to ignore that part. Okay, so to define the geometry of a truss structure, obviously we need to know, where are the joints and how are they connected. So in terms of defining the joints or the nodes of the structure located at kind of like the connecting points between these individual members or elements, all I have to do is just define where are they located in space. So I have to choose a coordinate system, some kind of global XY coordinate system in the case of a two-dimensional problem, and I just have to list off the coordinates of these individual nodes by their X and Y coordinates in that space. And that's all you really need to do. If you wanted to, you could pack that list of nodal coordinates into the format of an array, as I've shown here, where each row of this array nominally corresponds to a given node index or ID. And the two columns in this case correspond to the X and Y coordinates respectively of each of these different nodes. In MATLAB, it might look like this, a two-dimensional array. And there's nothing to say that I couldn't generalize this to accommodate three-dimensional trusses. So if I wanted to, let's say, include an additional Z coordinate, all I'd have to do is, tack on an extra column here in this vector, or rather in this array, and I could define a three-dimensional space truss, as they call it. Otherwise, two-dimensional planar trusses just have two columns. Okay, so that's just defining the nodes. And implicitly, I've also assumed that each one of these nodes has a corresponding node ID or a joint ID associated with it. And that's important when we're trying to define the elements and how they're connected together in this structure. So much as we did in the case of these one-dimensional finite element problems, we define an element by saying, what are its terminating nodes? And we do essentially the same thing in defining the connectivity of individual elements. We just say, let's say for element 2, its terminating nodes are 1 and 3, and so we can list those off basically as a pair of joints in this kind of array. Now, a good question that I'll pose to you is, this looks pretty much exactly the same as, that connectivity array that you would have in homework number 2 for these one-dimensional finite element problems. It's just kind of proportional to the number of rows being the number of elements, and each of the two columns are the two joints associated with that element. Does it matter, though, the order of how I list off these nodes? Just kind of think about it for a second. What do you think? Does it matter? Yeah, it actually it ends up not mattering in this case. If I were to, let's say, take this element and kind of like flip it over on its side and kind of like reverse its orientation. In the end, I haven't really changed the behavior of the structure. So that's correct. Actually, it doesn't matter which one you choose. It doesn't necessarily need to be, the smaller of the two indices and the larger later. But in any case, that's just kind of a small observation. Also, I have to list off, obviously, the geometric and material properties, much as we did for kind of like these one-dimensional problems. So otherwise, the way we define elements is very much the same as we did before. Just define the connectivity and define the material and cross-section properties for the elements. Okay. Now, yeah, go ahead. Was there a question?
But you said that there is no problem between like the exchanging 1 and 3 and 3 and 1. But if we have like a constraint in 1 or 2 or 4, that will change, no?
So it depends how you're actually going about prescribing boundary conditions. So if we're prescribing boundary conditions to the nodes directly, which maybe segues into this next slide, those constraints are imposed kind of on the nodes necessarily, but they don't necessarily pertain to the elements. The elements can be rearranged or reoriented with like different connectivity. But in the end, when we assemble our system of equations, we'll be kind of eliminating rows and columns or kind of partitioning our system of equations on the basis of how we've kind of assigned degrees of freedom to the nodes. So the elements could be rearranged and kind of flipped around. What really matters more so is, how have we numbered the nodes in terms of how the ordering of degrees of freedom appears in our system of equations. So on that subject, on the subject of constraining degrees of freedom in our problem, if we have a two-dimensional truss structure in this particular example, each node obviously can displace in either the x direction or the y direction. If it was a three-dimensional problem, there'd also be an extra z coordinate or a z displacement that node could experience. And basically what that means is that we have essentially, some number of nodes in this problem, 4 in this case, times basically 2 degrees of freedom per node. So in total, we have 8 degrees of freedom for the whole structure. And we can constrain any of those 8 degrees of freedom. But to do so, there are many ways that you can identify them. You can individually label those degrees of freedom and just kind of list them off. Like this is degree of freedom 1, this is degree of freedom 2, and then kind of like go joint by joint and kind of do that sort of labeling explicitly. Or you can kind of do it by first saying, if I'm going to try to constrain one of these displacements, I need to know which node am I constraining. I need to know which kind of direction am I constraining it in, and by how much am I displacing it, if at all? And those 3 things are enough to basically say, how am I imposing constraints, potentially multiple constraints to different nodes in the structure. So in this case, I can list off, let's say, through these 3 separate arrays, those 3 different things that I listed off. I can constrain a particular node. In this case, let's say node 1 is kind of listed here. I can also constrain, let's say, the first degree of freedom associated with that node, where maybe I associate kind of a degree of freedom ID or index associated with the X, Y, and Z displacement components of a given node. So I'm kind of like sub-indexing for a given node its different degree of freedom components through these indices 1, 2, and 3. If it's a two-dimensional problem, it's just 1 and 2. So I can say, let's say node 1 has its first degree of freedom or X displacement constrained, and I can prescribe that value to be equal to 0 if it's a fixed support or if it disallows displacement in the X direction. Same thing if I wanted to incorporate this constraint, a constraint of displacement in the Y direction, I can say node 1 also, again, has another degree of freedom, its second degree of freedom or displacement in the Y direction constrained to be equal to 0. So it disallows Y displacement. Same thing, node 4 has its second degree of freedom or Y component constrained to be equal to 0. So I have to list off these 3 different things. And obviously it means I could be constraining multiple degrees of freedom at a single node. So you might have kind of repeated entries for a given node being kind of constrained in different directions. So that's just kind of one way that you could go about defining these constraints in sort of this MATLAB context. And you'll see in homework assignment 3 that this is pretty much exactly how we're going about defining these constraints. If I wanted to assign, oh yeah, question here.
No, so just the vector of nodes not nodes of displacement. Can we just like put the value of the boundary condition in there?
Yeah, essentially that's what we'll eventually get to. And as I said, maybe that's kind of along the lines of what you're saying. If I said for this problem, uh, I could define it in terms of which node is constrained and which degree of freedom or local degree of freedom for that node is constrained. Alternatively, I could kind of maybe explicitly label these things with, particular degree of freedom IDs. So let's say in the global setting, maybe this is degree of freedom 1, 2, 3, 4, and I could list them off this way and basically say, I guess this would be 5, 6, 7, 8. There we go. Or I could kind of permute the ordering however I like. And I could say, degree of freedom 4, which ends up being, global degree of freedom 4 is the y displacement of node 2 in this case. You could prescribe that directly. So there's many ways that you could go about actually ordering or listing off the degrees of freedom for the problem as a whole. I kind of find it convenient, or at least that's kind of how I chose to implement in this context, to assume kind of an implicit ordering of these components or kind of like these labels that I'm assigning to the degrees of freedom in the structure, such that I can kind of index over them in sort of a clever way. But basically, I can say that the degree of freedom, let's say, associated with a particular node or something, the global degree of freedom ID, can be determined sort of from a formula. If I know which node ID am I looking at, let's say node 2 or something like that, I could say, let's denote this with, I don't know, node index I or something like that. And let's say I also happen to know that I want to constrain a particular local degree of freedom index, which I'll call maybe local degree of freedom index 2, or the y component of this node. I could call this, the second local degree of freedom for node 2. I'll call that j or something like that. And in general, I could kind of swap this and say I equals 1 if I'm looking at node 1, and so forth. That's basically what these two kind of rows are kind of denoting, an I and a j, basically. So node ID and a local degree of freedom ID. If I wanted to know the global degree of freedom ID in this kind of implicit numbering scheme, then basically I could say, well, there's 2 degrees of freedom per node. And essentially, I can kind of like figure out what the global degree of freedom is, consistent with this implicit numbering scheme, such that I take, those 2 degrees of freedom, multiply by I minus 1, and then plus j. And you'll see that, I think I use this implicit numbering scheme throughout pretty much the whole kind of rest of that MATLAB script. So implicitly, this is kind of what's happening behind the scenes. But you can rationalize that this particular numbering scheme arises from this particular, choice of offsetting things. So I'll kind of encourage you to take a look at that in kind of more detail. But obviously, it implies that the way that you index and kind of order these degrees of freedom it becomes more complicated as you introduce more degrees of freedom per node. So, there's some challenges there. Does that hopefully kind of clarify some of the things? But ultimately, however you choose to do it is, kind of up to you. All right. So similarly, we can say if we want to impose forces on the structure or specifically to the joints, I can do a very similar thing. I can decide or say which node do I have some force applied to, which direction is that force applied in the x, y, or z directions potentially, and what's the value of that force, where positive values of forces are assumed to be kind of acting in the positive global coordinate directions. Negative values in this case are acting in the, let's say, negative y direction or negative x direction. So I can say node 2 has a force in the y direction. So node 2 force in the second kind of like global coordinate direction, and it has a minus kind of 1 meganewton, let's say. So acting downward. Yeah.
You wanted to assign a force that was going at an angle so that it was a component of both x and y. How would you do that at library if it's constant?
Yeah, so you would have to kind of think through how would I represent that, not necessarily as an oriented vector. Let's see. Yeah, let's maybe space. So rather than representing it, maybe you have a force that's acting in this particular direction at some kind of inclined angle. We'll call it theta, measured relative to the x-axis. You could represent that basically just in terms of its components. You'd have to break up that vector into, let's say, f cos theta and f sine theta, and then prescribe each of those independently to the component of force and y component of force applied at a given node.
So you could just, the node line, you could do node 2, node 2, node 3.
Yeah, pretty much. Yeah, you would have to say, if I do have, let's say, a force who has components in the x and y direction, you'd have to kind of say node 2 has both an x and y component. So you'd have to double list node 2 and then list off its individual components, x and y. Yeah, good question, though. And very good question also because I think homework assignment 3 has you do exactly kind of this procedure where you have to prescribe a force that's acting not necessarily in a particular global coordinate direction. Okay. All right, so with me so far kind of makes sense. I think obviously thinking in this sort of multidimensional setting gets really interesting, but ultimately, once we have all this set up, it doesn't get too much more challenging than kind of what you've seen in the past. All right, so now we have to go about assembling our linear system of equations, which in parity with what we did for the one-dimensional finite element problems involved assembling our global stiffness matrix. This is probably the harder one of these kind of procedures. Assembling our vector of external forces. This is probably the easier one by comparison. And then finally, setting up our initial global vector of displacement unknowns. So for assembling the stiffness matrix, things get kind of interesting. Again, because we have a total of now, let's say, 8 total degrees of freedom in our structure as a whole, proportional to the number of nodes in our structure and the number of degrees of freedom per node. So you can kind of think of, in general, if we're assembling a system of equations, the size of the resulting stiffness matrix will be proportional to the number of degrees of freedom in terms of its overall dimensioning. So a number of rows and columns proportional to 8 in this case. The number of dimensions times the number of, or rather the number of nodes times the number of degrees of freedom per node is kind of the way to think of it. So in this case, if we're setting up our system of equations for assembling a stiffness matrix, all we have to do is dimension some kind of empty stiffness matrix that has the appropriate size to begin with, but initially we'll just set it all equal to 0 and then fill in appropriate entries through our kind of assembly process by looping over all the elements and then figuring out which entries of the stiffness matrix should we kind of enter in some of these summed contributions to the global system of equations. But the procedure looks very similar to the one that you would pursue in homework assignment number 2 for these one-dimensional finite element problems. We basically do this loop over all the elements in the structure. And then for each element, we have to determine its local element stiffness matrix. For a stiffness matrix of a truss element, as we saw in the last lecture, the size of that resulting element stiffness matrix is going to be 4 by 4. Proportional to the number of degrees of freedom associated with that element. So 2 nodes and 2 degrees of freedom per node in that element. Hence a 4 by 4 local element stiffness matrix, which we could compute in a few different ways. I think we provided 2 alternative expressions for how you could assemble a element stiffness matrix for a truss. One way that you could represent that is by supposing that maybe you have a smaller 2 by 2 array representing the effective one-dimensional element stiffness matrix of this kind of member whose length, cross-sectional area, and material properties are all known. So it's kind of that smaller 2 by 2 matrix that you would have explored in homework assignment number 2. But we have to left and right multiply this thing by these kind of transformation matrices. Essentially, these matrices are kind of like a coordinate transformation that takes our one-dimensional element, which is nominally aligned with some kind of local element, coordinate axis. And these transformation matrices kind of rotate that element effectively into the global coordinate system. That's kind of one way that you can interpret this operation. The other way is to just kind of write out the full 4 by 4 expression for a 2-dimensional truss element involving sines and cosines appearing in that kind of 4 by 4 array. So a few different ways you can do it, but the question becomes now, where do we sum these entries for this kind of local element stiffness matrix into the global array? And kind of maybe I'll kind of ask you, for element number 1, let's say, who has nodes 1 and 2, if we have already assembled the stiffness matrix for that element, which rows and columns should we sum this local stiffness matrix into in the global array? Hmm. Hmm.
Oh, that 4 by 4. I think it's 4 by.
Yeah, yeah. So basically, the first four rows and the first four columns correspond to the entries of the global stiffness matrix, where we're going to sum contributions for element number one, which has nodes one and two. Remembering that basically we've kind of assumed this implicit ordering of the degrees of freedom. And just for reference, I've kind of shown them here on the rows and columns of the stiffness matrix, so you can kind of, associate which columns are associated with which degrees of freedom, if you like. So column one is associated with the degree of freedom corresponding to x displacement at node one. Similarly, the second column is the y component of displacement at node one, and so forth. So if we're interested in all the degrees of freedom associated with nodes one and two, really that encompasses, these first four columns. So the x and y displacement components of both nodes one and two. And this is really dependent on how I've chosen to implicitly number these global degrees of freedom. If I'm using that indexing scheme that we discussed a moment ago, then this is exactly what the ordering should look like. And it makes things a little bit easier to figure out where should I plug in entries in the global array. So ultimately, I kind of identified that these are, in fact, as you point out, the correct entries where I would sum these entries into the global array. You could think of it, if you like, as having these sort of block structured entries, where each kind of 2 by 2 sub matrix encompasses kind of all the degrees of freedom associated with a given node. In this case, this first kind of 2 by 2 entry is associated with, the degrees of freedom associated with node one. So if it makes it easier to kind of visualize where these entries should get plugged in, that's kind of one way that you can think of it. So all we have to do is just loop over these kind of different elements. We also have to determine the orientation vectors for these elements, but we can just determine that based on the nodal coordinates. I think we provided some formulas for how you can compute that in a few different ways in the previous lecture. But ultimately, we just kind of loop over each of these elements, noting that if we're given the connectivity of these elements, we know which nodes terminate that element. So element two has nodes one and three. So correspondingly, it gets summed into these corresponding entries associated with nodes one and three. And you can rationalize which rows and columns of the stiffness matrix that works out to. So similarly, for element three, it's kind of these rows and columns. Nodes, or rather kind of elements 4 and 5, you can kind of work through the process of figuring out exactly how that gets summed in. But again, I'll encourage you, this is sort of the exercise that you're going to go through in homework assignment number 3. I'm asking you to do this process of assemble the stiffness matrix for a truss. So that's kind of the challenge that you'll be presented with, going through this process yourself and figuring out how to do the indexing and how the global degrees of freedom relate to the element's local degrees of freedom, and which entry should you sum the local stiffness matrix into for the global stiffness matrix as a whole. Okay. Any questions on this before we move on to the next? All right. Okay, so slightly easier for defining the external force vector. Again, it should be dimensioned to be a vector of size equal to the total number of degrees of freedom in the problem, in this case 8. And to figure out which entries in this array should I kind of enter these different components of applied force, all I have to do is say, well, this particular force, let's say applied to node 2 in the minus y direction, corresponds to global degree of freedom 4, basically the fourth entry in this array. So if I have a prescribed value for that force, I just plug it directly into the corresponding global degree of freedom index in this kind of vector of external forces. And you can kind of rationalize for this particular degree of freedom, node 3 in the x direction, that's kind of global degree of freedom 5. So it gets entered here. Okay. So again, assuming that implicit ordering, but otherwise just directly plugging in these applied forces in the x or y component directions. Okay, so as for applying, displacement boundary conditions, it's essentially the same thing. We initially assume that the displacements are 0, or at least, we could prescribe them to be anything we like at this point because we're going to solve for them eventually. But it's easy enough to just say dimension an array to be of size, 8 by 1 as a column vector, and then plug in any prescribed values of displacement corresponding to, where these different global degrees of freedom are kind of like appearing in this vector. So let's say, prescribing the y component of displacement at node 4, that corresponds to a global degree of freedom 8 in this kind of whole array. So that's where you'd plug those in. So it makes sense so far, kind of, at least conceptually. All right. So probably the most challenging thing about this, in my opinion, is the indexing. There's a lot of bookkeeping and kind of figuring out where things get plugged in. MATLAB, there's a few tricks that you can use to implement this in a MATLAB context that make that process easier, but I would say that's probably the one thing that could trip you up on this. All right. So now we've assembled our system of equations. It turns out that the process for partitioning and solving our system of equations is almost identical to what we did in the previous kind of lecture on Friday. So there's really not too much that I want to go into here other than to say, I'm not asking you to go about doing this partitioning process or to invert the stiffness matrix or do any of that in the MATLAB coding. All of that's kind of in there already. I want you to focus mostly on assembling the system of equations. Just know that essentially the process for partitioning the system of equations and solving it looks entirely identical to what we talked about last Friday. So all you have to do is identify which degrees of freedom are constrained, which degrees of freedom are free, and then kind of rearrange the degrees of freedom in the stiffness matrix and these vectors of unknowns and external forces in order to kind of permute that system of equations into a block-structured format that looks kind of like this. And then the procedure for actually solving that system of equations is just 2 lines in MATLAB, basically. So, doing that same kind of procedure that we talked about. And mathematically, these statements look identical to the statements that we presented for these one-dimensional problems. Once you've formatted everything into just a problem that involves inverting a matrix, which may have been partitioned into a block structure, really, it doesn't matter what the structure looks like. It could be a one-dimensional structure. It could be a 2D truss structure, a 3D truss structure. It could be, any number of things. Once it's in this algebraic kind of linear algebra format, MATLAB doesn't care about the specifics of what that matrix represents. It's just saying, well, I'm doing this linear algebra operation. I'm inverting some matrix, not necessarily a stiffness matrix, and it's multiplying some vector. It's coming from somewhere. But at this point, it's really just more about the algebraic operations of manipulating the system of equations, which could be representative of really any kind of structure or any kind of linear system of equations. So that's kind of why I say you need not fuss over these kinds of details. At this stage, yeah, go ahead.
Is the backslash and forward slash in MATLAB, do both work if you want to, if you wanted to put the K at that first, you forward slash for the denominator?
So it is interesting. I think that they are slightly different, actually. So the interpretation here that I'll give is actually, the MATLAB documentation would probably be more thorough. But supposing I had some kind of matrix and I wanted to do something equivalent of, K inverse times F or something like that. In MATLAB, it would look kind of like the use of this backslash operator. So I have to do something that looks like this. So indeed, consistent with that, if I tried to do this, if I said K forward slash F, then yeah, unfortunately, this doesn't quite work. It might work if you tried to do kind of the reverse, if you did F divided by K. Really, the intention here is that if you have something that looks like this, and if you assume that these were not matrices or vectors or anything like that, this would end up looking something like F, just a single number divided by K, right? Which is kind of what you're trying to work towards. Similarly, this expression kind of implies that F should be divided by K. So you're kind of trying to get an expression that resembles that. So the orientation of these kind of slash operator is important for ensuring that you have something that kind of resembles this form.
But is the third one you wrote, would that work?
So this expression actually is potentially different. So if, let's say, I'm trying to do K inverse times F, that would be appropriately represented in a MATLAB context as K backslash F. But actually, this operation, F divided by K, at least if F is a vector, K is a matrix, this would look something more like F times K inverse, which is, you would think maybe this is the same thing, but actually it's slightly different. It depends on kind of the dimensions of these arrays and things like that, and whether or not K is symmetric. In our case, K is symmetric, so I think you would probably get a similar result, but you might have to do something like transpose this thing or something like that in order to get the matrix vector dimensions to work out correctly. So this is very interesting, good questions, very insightful questions. Yeah, these are things, I didn't belabor this because, I wasn't too sure if it would hold much interest, but I'm glad that you asked these questions if you're interested in MATLAB and some of these details. All right, so other questions on this before we kind of skip to the next part? Yeah, again, I'll just reiterate, once you kind of have the system of equations set up, the process for solving it is very generic. And that's what's really exciting about the finite element method is it really allows you to implement these kind of different elements in a way that basically preserves a lot of the same implementation for the other components of the numerical solution procedure. Really, a lot of the interesting things, the things that pertain to how you discretize the structure, all that stuff is kind of more done in defining the problem and assembling the system of equations. But the actual linear algebra behind solving and setting up the, actually partitioning equations is, that's all behind the scenes. You can modularize that in kind of an algorithmic context. All right, so once we have that, we've solved for the displacements of the structure, but again, that's not really the thing that we're interested in. If we're trying to analyze the structure and maybe design the section sizes for the individual members, what we want to know is maybe what are the internal forces in a given truss element. And to do this, we kind of have to come back after the fact and compute what are the internal forces in the structure almost as a post-processing step. So once we know what the displacements are for each one of the nodes, we can come back, loop over each individual element in the structure, and then figure out what are the states of internal strain, stress, and force, given that we now know what the displaced state of the nodes are. So again, we're kind of working through that forward sequence of relationships. Knowing displacement, we can figure out everything else. So we apply just these basic equations from mechanics, relate displacements at the nodes to the corresponding strain in a given element, using this relationship that we derived in the previous lecture. Assuming small displacements or small deformations, you can come up with an expression for the strain or axial strain in a given element that depends on the overall length of the element, as well as it depends on the element's orientation vector. So we have to basically take this element orientation vector as a vector of unit length aligned with the axis of that element. And if we want to know the axial displacement of each of the nodes relative to that element's local coordinate system, then we have to take the dot product or the projection of each of those nodal displacements onto that corresponding unit vector aligned with the member's axis. So that's why, the ultimate expression for the strain looks kind of like this, a little bit different from the case of one dimension, because we have to do this coordinate transformation or projection onto the element's local coordinate system. But apart from that, everything else looks the same. And this procedure ends up being not so bad. Again, in general, you're not necessarily going to be given things like what are the angles of inclination of individual members or their overall length. You'll generally be working with coordinates of the nodes. And from that information, you have to surmise, what's the overall element length or what is the element's orientation vector. So that's kind of why I'm showing here. In practice, this is how you would do it in the algorithmic setting. And again, this particular implementation, this particular function is something that I've asked you to implement in homework assignment 3. So similarly, you'll have to go through these steps, but it ends up being actually fairly direct. Okay, so once we have all that, all we have to do is just kind of interpret the results. We've implemented things in the MATLAB code. We can kind of read off what are the internal forces in some kind of like output that gets fed out to the command line or the terminal in MATLAB, but that's not very appealing. It's kind of hard to interpret. The better approach is to visualize the results. Now, the overall program that I'm giving you for homework assignment number 3 encompasses a few additional functions that kind of make it a little bit easier to define different problems and to display the resulting problems in kind of a more visually interpretable way. So the main program is called Truss elements.m. It's kind of like the main driver script, but it calls these other functions accordingly. I'm asking you to implement these 3 functions: assemble the stiffness matrix, assemble the vector of external forces, and determine the element's internal state or the internal forces. So hopefully, it's very similar to what I'm asking you to do for homework assignment number 2, just for this kind of 2-dimensional or possibly 3-dimensional truss structure. It's okay if you just want to do it for only 2-dimensional structures, though. All right, so otherwise, the defined problem kind of script I also, in some of the problems for homework 3, ask you to dive into this one and maybe modify some of the definitions for some of those problems. So you kind of see how those definitions relate to the setup and solution of these different kind of truss structures. And the display problem, you don't have to look at this. It's just a bunch of like MATLAB behind the scenes, drawing figures and things like that. But it helps to visualize some of the results. So when inside of this truss elements.m script, there's kind of like a problem name that's being specified as just kind of like this input string. And that string is essentially being fed to this define problem function. It's the only input, and basically it specifies a particular problem corresponding to an already implemented problem definition contained in this defined problem script. So you'll find in that script actually a bunch of different predefined problems like this. For example, the king post example corresponds to this particular structure, the one that we've kind of been considering in all the demos of like the prototypes of how you would define forces and boundary conditions and elements and nodes in that kind of simple two-dimensional truss example. So all you have to do is basically go to that problem name, write in king posts, and you'll get this particular problem. And not only will you get this problem, it'll show you the problem setup. So how are the forces defined? How are the boundary conditions defined? So you can verify that everything was defined correctly. It looks okay. You can kind of also visualize the coordinates of the nodes, make sure they're positioned correctly and the connectivity of the elements. And when you run this MATLAB script, the main kind of like truss element script, you'll get some visualized outputs. You'll see some of the reaction forces at the different nodes shown in green, in addition to the externally applied forces. And you'll also visually see how the internal forces in this truss arise. Tension is in blue and compression is in red. So the darker the color, the more intense, or the larger the apparent value of internal force. Similarly, you can visualize the displaced state of the structure. So the dashed line is the undeformed state of the structure, and kind of like the blue magnitude shows the magnitude of the overall displacement of individual joints. So you can reconcile that, under these applied forces, this structure definitely looks like how you would expect it to look after you put these forces on it. If I'm putting a force, in the minus x direction here, certainly this node should be displacing in the minus x direction. Same thing if I'm pushing downward on this node number 2, we expect it's going to be displacing downwards, but the rest of the structure is doing some other interesting things. So again, this is all very useful if you're trying to just verify your implementation is correct, and also if you're trying to, let's say, design the structure. I included, I think in homework assignment number 3, kind of a design problem. So homework assignment number 3, problem number 4, gives you an opportunity to try to design an optimal truss. So it's a bit of a flavor of a structural optimization problem. And there's several ways that you can solve that particular problem. But I kind of ask you to try to iteratively change the cross-section properties of the different elements in a given truss design in order to kind of minimize some objective cost function. So you can play around with it. You can do it iteratively. You can kind of do a guess and check procedure, or you can try to automate it. Given that everything is implemented in MATLAB, you can maybe try to create an external driver script that kind of over different possible solutions. There's varying degrees of complexity that you can employ to try to solve those problems, but I'll let you have fun with it and kind of explore that. But this is really the advantage of having an automated procedure for solving these problems, is that the time to solution is so short. You can change one small aspect of the problem, and then all of a sudden you get an answer and you can decide, how should I modify my design to better satisfy maybe some objective. Okay, so let's actually work through a few more of these examples and kind of reinforce your intuition. The other benefit of having this sort of automated way of solving these truss problems is to really help you develop a better intuition about how structures behave. And trusses, in my view, are kind of a good candidate for reinforcing that intuition because they offer kind of like a nice way for you to visualize the result and kind of understand how forces are going to distribute through a given structure. So just as an exercise, let's kind of go through a few of these examples, and I'll ask you to decide which of these forces are going to be in a state of tension, which ones will be in a state of compression, and perhaps which ones have zero force in them. So it's kind of a fun exercise, perhaps even an exercise that might show up on an exam, but it's one I think that kind of is helped by having these results that you can kind of test your knowledge against. So for this example, let's suppose, I have the forces as shown here, supports as shown here. What do you think the internal forces are going to look like in this structure? Feel free to shout it out. Well, maybe we'll go member by member. What's this vertical member going to be? Yeah, sure, compression. What about this one, the diagonal?
Compression.
Probably also. And then this bottom member,
Compression.
you say compression. What about these? The top member.
The right one would be a tension. Yeah.
And the top one? What do you think? I mean, this is a tricky one.
There will be no internal force on the top one.
Zero internal force. You said zero force. And what's the rationalization for that?
Because there is no load. The load can freely move when the load is applied. So
Yeah. There's probably a few different ways you could rationalize what's going on here. But ultimately, if you took a look at this particular joint, and you could do this just from like basic statics, if we looked at this particular node, and maybe did kind of like a small kind of method of joints kind of approach, we could note that there's going to be internal forces in each of these two members that are potentially pulling or pushing on this joint, but they're completely orthogonal. They're not necessarily coming in at the same angle. So if I were to take sum of forces in the x direction and sum of forces in the y direction at this particular joint, I'd find that there's, sum of forces in the y direction, there's only this one force. There's no other external forces that could balance with it. So the only way for this joint to be in a state of equilibrium is for this force to be zero. And you could make the same argument about that x-directed force. So indeed, we find that those top two members are going to be zero force members. As for the other members, what we find is, certainly these two vertical, members are going to be in a state of compression. That makes good sense. If we have a force here, it's pushing down. This, member is also kind of being pushed to the right because we have also an extra force here and a force pushing down. The bottom one is in tension, though. So what's the rationalization there? Why is that one in tension?
Because the diagonal member is in compression.
yeah, so it's to balance the.
Yeah. Again, it helps to kind of go back to your classic statics and think of in terms of that method of joints approach. If we know that vertical member coming into this bottom right joint, let's say that's constrained here, it's going to have maybe a reaction force pushing up. It's going to have, again, maybe some compressive force pushing in on this joint. So really, there's a few different ways you could rationalize this, but sum of forces in the x direction requires that this force pushing this joint to the right has to be balanced by some kind of tensile force pulling the joint backwards or to the left. So that's kind of one way that you could rationalize what those kind of internal forces should be, kind of recollecting how, the method of joints gets applied in this context. So that's not so bad. All right, what about this one? This one maybe is a little bit easier. What are the internal forces for all the top members? Let's say these three members on the top of this truss.
Compression.
Yeah, and the bottom members.
Tension.
And then these internal members.
Could be compression.
Well, that's a good question. What do you think? If you had to one way or the other, tension or compression, maybe one's tension or one use the other. Well, let's try good old statics, right? This is probably a good refresher. If we're looking at this bottom joint, we have a downward force here. Ultimately, we've said that these are going to be tension, okay, or at least that's our assumption. What would the force have to be in each of these two members if this joint is going to be in a state of equilibrium? You say compression?
This is going to point up.
Pointing up, yeah.
Yes.
So in other words, it's got to be in tension, right? And what should be the relative magnitude of each of these two different forces? The same or different? Yeah, the same. And the argument here is symmetry, right? The structure is symmetric, the loading is symmetric, which kind of implies that the internal forces distributed throughout the structure should also appear to be symmetric. So we can kind of rationalize that about that plane of symmetry, the internal forces should all look the same. And that's kind of what we end up seeing. It might also help to kind of visualize how the structure is going to deform to help you visualize which of these kind of members are going to be in compression versus which ones are in tension. You know, members that are shrinking in size or, you know, obviously shortening, those are going to be in compression. Ones that are elongating are going to be, you know, obviously put in a state of tension. Another way I kind of like to visualize this is if I have a force hanging down on these two members, then I would think that's going to kind of pull them or kind of elongate them. So hence, I would think tension. That's kind of the probably quick and dirty way to estimate that. All right. Yeah, here's another one, a little bit of a fun one. Let's see. We'll do the easy ones first. What do we think the top members are going to be? Compression, bottom ones probably by extension or tension. Now the tricky part is, what about these vertical members or kind of these interior diagonals?
Zero force member. The yeah, the diagonals are zero force.
Yeah. Similar reasoning behind that. I think if we have two forces that are supposed to be balanced with each other here and here, and we have just kind of like one, you know, force that's kind of acting in a direction that's perpendicular to those two members, there'd be no other force that could balance with whatever force is coming in from these members. So they do have to be zero force. Good observation. And then this vertical member has to be
Compression.
well, think back to the previous example. Yeah. It'll be a very similar rationalization for why this vertical member should be tension based on kind of our previous example. So vertical force pulling down, so this kind of middle member has to pull back up. All right, here's another kind of fun one. All right, so I think I don't have to ask you, but probably compression on the top, tension on the bottom. Really, the interesting ones are what's going on with these internal members. So what do we think? What are the, you know, it's symmetric, so at least we know that it's got to look symmetric, but what are the internal forces here? Yeah, intuitively, I'd say, you know, I'd want to say they're all tension, right? You're shaking your head though.
Think the two diagonal members, the middle, one is in tension, one is
Well, could that be possible?
no, because it's symmetry.
Yeah. Because of symmetry, we can't have kind of like, and because the loading is symmetric. If the loading was not symmetric, then, you know, anything's game. But in this case, you know, what do you think? Tension or compression for these middle ones? Compression, tension. Intuitively, based on the previous examples, I would want to say tension, right? Just because like that agrees with this joint's moving down. It would seem like these are elongating, right? The answer will surprise you. They're zero. But why?
Because the top, because the top is straight, so the forces are balancing on the top, and we don't need those extra branch.
Yeah. Ultimately, I think that your rationalization in words, you know, I think is more or less what I'm going to reiterate in kind of this pictorial representation. If we have only, you know, like say compressive forces along the top, but we're trying to figure out what are these forces here. The problem is we've said due to symmetry that they can't have opposing directions. So this is not allowed. They have to both point either up or down. But if they do that, then they can't be balanced by any external force. So we find that that's just not admissible. So the only way that this joint could be in balance is if they're both zero. So zero force members there. And, you know, there's a few extra things that I'll point out here. I'll just note that this particular program is implemented so that you can visualize things in 2 dimensions for simple 2D planar trusses. It also works in 3 dimensions. So go ahead, give it a try. You know, this is just a very simple kind of 3-dimensional or space truss. And it turns out the implementation for, you know, a 3-dimensional truss is really not at all more complicated than that of a 2-dimensional truss. You just have an extra degree of freedom per joint. And maybe the computation of the element stiffness matrix is a little bit more challenging, but otherwise it's kind of fairly direct. All right, so that's all we have time for today. Again, if you have questions, feel free to visit in office hours or immediately after class. Otherwise, I'll see you on Friday, I guess.